put them online, and we'll send out links to the recordings when we have them.
Yes, we're also asking for like, if they want to share slides or notes or any other resources, like we've already gotten a Mandelbrot set like generator, right? Like that's gonna get sent out to you, just a list of resources for talks. So I think that's really nice. If you've thought of something you think should be associated with a talk, you should also email us so we can send it to other people.
Notably, if you decided to show up on a whim today and didn't register, we're happy to have you, but you're not going to get any of these emails. So just fill out the conference registration form very quickly, and then we'll add you to the participant list.
Yeah.
But do it today. Otherwise, that's everything.
Do we do our just thank you for coming? Like, we're so happy to have you.
And we also want to thank AIM, who has provided a healthy dose of funding for this, along with NSF. Yeah, this is technically part of an AIM research community.
Somewhat. Partly. We did some stuff. We figured it out.
Yeah.
But yeah, this is great. We're happy with how it's going, and I'm so glad I could meet so many of you.
Yeah. Okay. Now it's my pleasure to introduce Sully Coles, who will be talking about knot invariants and hyperbolic flows, joining us from up north in Evansville.
Thank you. But before you go, as the last speaker, I should thank the organizers. And there is another organizer somewhere.
Laura is not.
Okay. Anyway. Thank you. Okay, so I think I have this clicker now working. Yeah, so like Ben said, I want to talk about knot invariants and hyperbolic flows. So the base of this talk is a bit of fun, really. A hyperbolic flow is a continuous dynamical system that is supposed to be chaotic. That makes me think of a tangled bunch of flow lines, and I want to actually quantify how tangled they are. Okay, and I'm going to use knot invariants to do that. Okay, so just a quick outline. Does the clicker work? Yes. Okay, so it's going to be the usual thing. Some background, the main objects that I will use, some previous results that do the main stuff, and then new results where I just copied their results and changed it a bit. Okay, this is the idea. Okay, so first I'll tell you what hyperbolic flows are. So I want to start with a hyperbolic splitting, but maybe, okay, I'll give some intuition first. You've maybe heard geodesic flows talked about a fair amount over the past couple of days. These are like the generalization of the generalization of a geodesic flow. Okay, so geodesic flow got generalized to an Anosov flow, and an Anosov flow got generalized to an axiom A flow, which is something that has this sort of hyperbolic behavior, but on a closed invariant set that doesn't have to be geometrically nice. Okay. Okay, so I'm going to work only in 3 manifolds, and phi t is going to be my flow, and I'm going to need a name for the vector field associated to the flow. That's going to be x. Okay, so what is the hyperbolic splitting? Well, a closed invariant set, lambda, is hyperbolic if there is a splitting like this. The tangent bundle splits into 3 directions. One is ES, which is stable direction. One is just the direction of the flow generated by the velocity field. And the other one is EU, which is the unstable direction. Okay. So what do I mean by stable and unstable? If I'm moving forward in time, so if t is positive, then the derivative of the flow is going to expand vectors in the unstable direction. It will contract them in the stable direction, and it will do so exponentially fast with this parameter t. Okay. I believe I have a picture. Yeah. Okay. This is the picture. So the curve is a piece of flow line. Sitting on top of a point on this curve is a tangent space. The tangent space has 3 directions. One is tangent to the flow, and the other 2 are the unstable and stable. If I take an unstable vector, it gets much longer under the derivative. And if I take a stable one, it gets much shorter. Okay, so this is the picture. Okay, The reason these hyperbolic sets are sort of supposed to be chaotic, have chaotic dynamics, is because when you have this expansion and contraction, it means you have very sensitive dependence on initial conditions, right? So if I pick a point very near my point P, it could exponentially diverge in orbit. It could exponentially converge as well. So there's two different types of behavior going on. There's something else we ask for a hyperbolic flow. We want our set to be basic, which means the dynamics is transitive, there's a dense orbit. The periodic points are also dense. And this other thing, which I think of as the set kind of behaves like an attractor. Okay, so there is an open neighborhood of this set on which it's just the intersection of all the images of that set. Okay, another picture, hopefully. Oh yeah, okay. So then the flow restricted to this hyperbolic basic set is called a hyperbolic flow. Okay, and the whole flow in this case will be an axiom A flow. So this is a picture of M, and an axiom A flow is one where you have this picture. So you have a finite collection of these basic hyperbolic sets where nearby dynamics is attracted to them, and inside them you have this hyperbolicity. Okay, just another thing to point towards this idea of chaos. The fact that you have a transitive point and you also have dense periodic orbits means in any very small, like open neighborhood, there is a point that goes everywhere, and there is a point that comes back in finite time. Okay, so this is again two very different types of behavior inside any small thing. Okay, so that's why we ask for these things. It's not just fun that we want to put all these conditions. Okay. All right. So I'll give you the example that I mentioned at the start. Okay, geodesic flow. So I want a closed connected hyperbolic surface. I take a unit tangent vector. It gives me a bi-infinite geodesic, and I just flow the vector along that geodesic, and that's my flow. Okay, this is the kind of prototype of a hyperbolic flow. So in this case, the basic set that I'm talking about, there's just one of them, and it's the whole manifold. Okay, and that's what we call an Anosov flow. And then if you kind of forget about respecting the geometry, you get the kind of flows that I'm talking about. Okay, so just the general hyperbolic flow. Okay, so that should probably be that for the dynamic side of things. Yeah, okay, so let's say in this talk, I'm pretty much only going to talk about when the manifold is the three sphere. Okay, so I said I was measuring tangledness, and I was going to use knot theory to do that. The kind of the basic case for knot theory is the three sphere or R3, which will be thought of as basically the same thing, especially because yeah, for us, we will actually be working in a proper subset of S3. I'll say that in a second. So just some results so that we know where we are. A result of John Franks says, it says something more precise than this. He didn't just write a paper that says this at the top. Okay, there are a lot of these things. Okay, so that I can't really write one down. It's not very easy, but there are lots of them. Okay. There are as many hyperbolic flows as there are subshifts of finite type, for example. Okay, so he showed that yeah, any sort of suspended flow over a subshift of finite type can be realized as a hyperbolic flow through this coding that Nima was talking about earlier. Okay, but yeah, okay, but in this case, we can't have an Anosov flow. This is also, this result is also deeper than the sentence that I wrote. Okay, this is a result. Oh, actually, I've made an issue here, which is that I've mentioned Thurston, which many people have mentioned. This talk will actually feature two Thurstons. So this is grown-up Thurston. Okay, later on will be Dylan Thurston. Okay. Okay, but so we can't have lambda being the whole of S3. Okay, it's not possible because that would mean I supported an Anosov flow, and to support an Anosov flow, you have to have a fundamental group with exponential growth. That's the result of Plant and Thurston. So yeah, this is not the case. Okay, so for us, yeah, lambda is a proper subset of S3. So I'm really just going to think of it as a set in R3, right? S3 is just R3 with an extra point. So if I have a proper subset, I can always rearrange things to just pretend I'm in R3. And that's where all the knot theory can be done pretty easily. Okay. Yeah, so this is the motivating question. How tangled are the orbits? Okay, you can interpret this in several ways. I might mean how tangled are different orbits with each other, or how sort of eccentric is one orbit. Okay, but I'll be thinking of periodic orbits in particular. And what we do is we measure this tangledness using invariants or different quantities from knot theory. So I'm just going to give now a little overview of what I claim people in knot theory do, but if there are any people in knot theory, like, keep quiet because I assume you do much more complicated things. Okay, so a knot is just an embedding of a circle in your space, okay? In this case in R3, but in general, in any 3 manifold, sometimes 4 manifold, but let's not worry about that. If you really want, this comes with an orientation. Just if you go clockwise around the circle, you get an orientation of this embedding. So this is the picture. This is called a knot diagram. So this is a trefoil knot sitting in R3. And this is what the diagrams look like. So they have crossings where you are indicating that one piece of it is going over another piece. Just imagine a piece of string that you have done something to and then glued the ends together. Okay, that's what a knot is. And just like you would with this piece of string, we think about them. Oh, I should say this first, sorry. So an n link is just n of these things that I just joined, okay? And I have some notation. Ln will be the space of n links, and K, which is just L1, will be the space of knots, okay? But yeah, people consider knots up to isotopy. Okay, so you take this piece of string that you have and you're allowed to do whatever you want, but you cannot push it through itself because that's not how string works. Okay, so this is a picture of an isotopy, and you can see that, like, you know, if you isotope something, right, it has the potential to get more and more tangled, right, without sort of changing its inherent knot properties, and so one of the things that these invariance functions that are invariant under isotopy, one of the things that they measure is kind of a certain type of tangledness. Okay. Yeah, they often measure tangledness or intertwining. I'm going to try and stop saying the word tangledness so much because it's not going very well for my mouth. Okay, so I think now, yeah, I want to talk about the sort of first example of a knot invariant that maybe people see, which is the linking number, okay? So this is just literally how many times one curve wraps around another one. So I have 2 knots, and they might do this, and I would say they're linked once, but if I could do this with my hands, which I can't, if it wrapped around twice, it would have linking number 2, okay? So that's literally what it is. You just look at the picture and you see how many times it wraps around. This is the formal way to do it, because there is a parity to it depending on the orientations. So you look at each crossing in this diagram, so each place where one knot goes over another one. And you're going to see one of 2 pictures. Either the blue thing is going to be, you know, behind the red thing, or it's going to be above it. You know, you can turn these pictures around, but those are the options, right? To either count +1 or -1 when that happens, and then you have the total, and this gives what we call the linking. Okay. I should make clear here Okay, this is a picture in R3, right? So I'm looking at it from a specific angle. Okay, like I'm looking at it from this angle. If I looked at it from over there, it would look a bit different. But the linking number is invariant under looking at it from a different angle. Later, we're going to talk about some other quantities that are not invariant under looking at it from a different angle, but they still kind of, yeah, they still can be useful. Okay. Anyway, this is the linking number. So it tells you how much one curve wraps around. That's literally it. Okay. There's a way to understand the linking number with an integral. Okay, so even though it's an obvious thing, you look at it, you see how many times it wraps around. You can find it out using an integral. So you look at this map, which takes it takes 2 points on the circle, T1 and T2, and it looks at the direction vector between time T1 on one knot and time T2 on the other knot. Okay, and then it projects that onto S2. Yeah, sorry, direction vector. So this function just says, what is the direction vector between the points on these two knots, right? Gamma and beta. Okay, and then the linking number is going to be the degree of this map. So it's going to be how many times this direction wraps around F2. And that's why I want to have this omega be the standard volume form on S2, because that's how you work out the degree of them. Okay, you take the wholeback of the volume form, and you find it. And it turns out that the linking number is equal to that. Okay. In some sense, this is the big idea of this talk. Okay, so let me write the full thing. So when you actually write this out as an integral, you just get an actual. I mean, I don't want to disparage people who like integrating differential forms, but you just get what I'm going to call an actual integral. Okay, like you could compute this in theory, right? Okay, so the reason this is the big idea is that before, when we just had a sort of picture, yeah, like this, and we were just looking at how things wrapped around each other, we weren't going to be able to study this number using ergodic theory, okay, which is my aim, by the way. I could be Nima-esque and call this ergodic topology if you want. Yeah, so what you do is, so what you do is you end up using this integral to rephrase everything in terms of integrating a function against certain measures, right? And this allows you to do ergodic theory if you have a dynamical system in the background. Okay, so for us, the knots we'll end up working with will be periodic orbits of a system. We will encode these with measures, and then finding the linking number will be integrating a function against these measures, which is something people know about. Okay, and that leads me to probably the first result that was kind of relevant in this area, which is a result of Contreras. But I should first give you some notation. So I have my hyperbolic flow in S3, and for a periodic orbit, gamma, the period is going to be L gamma. Okay, maybe I should have used like a P or something, but as I said, and as Nima said this morning, this all comes from the geodesic flow. Like all of this study of these sorts of things comes from the geodesic flow. So people often use L because it's length of a geodesic, right? But this is really a periodic orbit of some other system. Okay, so this is the period, and I want this set to be PT, the set of periodic orbits whose period is like between T and T plus 1. The interval doesn't really matter, just some fixed interval around T. Okay, and then again, following from Nima earlier, the most general form of this result I know is due to Parry and Polycott. There are plenty of other people, like Nima mentioned, that came before this, but in this setting, the number of periodic orbits grows like e to the entropy over HT because I'm considering prime periodic orbits. Okay, I'm not wrapping around multiple times. Anyway, I mean, this is not important. It's just to tell you that there are a lot of these things. Okay. Okay. So now the theorem. So I take a hyperbolic flow in S3 and the vector field is X. And I define this function, which if we remember our slide on the linking number, this looks very similar to the linking function, okay? The function that was inside the integral at the end, except in the like furthest right bit of it, I have the vector field of the flow, whereas before I had the derivative of the two knots, okay? This is because if I'm following a periodic orbit of my flow, the vector field will be the same thing as the derivative of the knot. Okay. So this is the function. What can you say about this function? Well, the theorem is this. So my hyperbolic flow has a unique measure of maximal entropy. This is a classical result, probably of Bowen. Okay. And it turns out that if you look at the average linking number over all periodic orbits of length approximately t and all periodic orbits of length approximately s, if you look at this average, which is the thing on the left-hand side, it grows like t times s times the integral of that function with respect to the product of the measures of maximal entropy. Okay, the constant, like the integral, in this context is not super interesting, but it's just to show you that you can write down the precise integral. In other contexts, the integral does get more interesting. So we generalized some of this work, me and my PhD advisor, Richard Sharp, to other manifolds where hyperbolic flows can preserve volume. And when they preserve volume, you can do a very similar thing. And the integral on this side becomes the helicity of the flow, which is something that if you care about fluid dynamics, you care about, but if you don't, then ignore me. The integral is non-zero. Yeah. So that should be said. Yeah. So this for sure is grown. In this case, I think in other manifolds, I think it can be good. Okay, so this is the theorem, and this tells you that on average, periodic orbits intertwine sort of quadratically according to that period, right? Okay, so that's a bit of fun. He's told you how much they wrap around each other. We essentially want to do the same thing, but for talking about a single knot rather than the linking of two, we're going to talk about how sort of eccentric one knot is. Okay, one periodic orbit, whatever you want. Okay, but I should tell you a bit about the proof of this, right? Just to show you that there is some dynamics. Nima wanted more people to mention thermodynamic formalism. I don't think I wrote that down, but the proof is thermodynamic formalism. So I defined some measures. The first measure I defined is mu gamma, which is the probability measure supported on a periodic orbit. So the measure of a set is literally just what proportion of gamma intersects that set. Okay. And then mu t will be the average of these measures over all the t periodic orbits. Okay. And now I'm just going to rewrite the quantity on the left-hand side as an integral against some of these measures. Well, almost. That's what I'm almost going to do. 1 over ts times the fancy L of t. I'm using a lot of L's in this talk. That's life. I was going to try and say something that makes it easier to deal with, but couldn't think of anything. So I'm using a lot of L's. This fancy capital L of t is asymptotic to this slightly different average where I divide by the length of the orbits. And this thing is equal to the integral of that L function with respect to mu t cross mu s. Okay. So essentially, if I can prove that this integral on the right converges to the integral with respect to the measures of maximal entropy, then I'll be good. I'll be done. And that's where all the work is, and that's of course the bit that I will hide in a second. First, I will say the measures do converge. Okay, so this is another classical fact of Bohr. In fact, this is how he proved that the measure of maximal entropy exists and is unique. Okay, and then I will hide all the rest of the work just by saying this. Okay, so we check that the function L is a nice enough function that these integrals converge. This involves showing that the function doesn't like blow up too much near the diagonal where it is not defined. Okay, so maybe I go back a bit so we can look at the function. If x is equal to y, this thing is a problem, right? So you have to show that this is not so bad when you get near to x being equal to y. This involves showing that the dynamics does something cool. That's all I'll say. Okay, so yeah. Okay, so now I just want to remind us of this integral version of the linking number, because we're gonna move on to something for a single knot that is basically defined in the same way. Okay, so I'm finding the degree of this map. And this is the map that tells me what the direction vector is between these 2 points on my knot. Okay, if I want to do this for a single knot, my goal is to define a kind of self-linking number. What I would ideally do is just put gamma in both places in the linking number, right? But you have a bit of a problem here, which is, you can't just look at a diagram anymore. It doesn't really make sense, right? If you look at a diagram and you look at the crossings and you do the same counting that I said, it now depends on which angle I was looking at the diagram from, okay? So we have to do something different. We have to use the integral definition. But now we get a problem, which is that this function, now it doesn't have 2 different knots. So on the what am I trying to say? When T1 equals T2, this is again not defined, right? So you have this problem coming up if you try and do it with 1 knot. So I'm only defined on the configuration space, which is C2 S1, which has 2 points in S1 that are not equal. There's your picture of S1 cross S1 without. There's your picture of this configuration space. Okay, so if I want to eventually integrate this function, I'm concerned because it doesn't look good near the diagonal, right? But you can extend the function to the diagonal, but it depends from which side you come. Okay, so if you come from the bottom, you get the direction of the derivative. That's what the function extends to. If you come from the top, or maybe it's the other way around. One way you get negative direction, one way you get positive direction. Okay, so just trying to extend this function so that I can integrate it is not going to work. Okay, so knot people, and I don't mean NOT people, I mean KNOT people. They decided to try and remedy this kind of situation by taking a different compactification of the torus without the diagonal. Okay, so instead of just trying to put the diagonal back in and extend your function, what you do is you blow up the diagonal. Oh yeah, sorry. You can, and this is essentially what you end up doing. Like in the end, everything turns out to be like the linking number of gamma with an isotoped copy of itself, but you have to average over many directions. But I will talk about that in a second. Yeah. Yeah. So we fix this by blowing up the diagonal. So that gives you this picture. So now it doesn't matter that I extend differently when I come from the bottom and from the top, because the boundary is now in 2 pieces. Formally, what you're doing here is you're replacing the diagonal with a copy of its unit normal bundle, right? So you replace it with just a gap in this situation. Okay? So this gives me a different compaxification of the configuration space, which is called the Fulton-McPherson compaxification, introduced in an annals paper, so it must be important. But I don't really know why. You should ask an algebraic geometer. Okay, but it is at least useful in this setting to allow us to still define the integral we want. Okay, so f now extends uniquely to this boundary, and we can define the rive, which is this self-linking number, as that new integral. Okay, but yeah, if this was just sort of annoying and like, come on, it's the last talk, why did you have to go into all this stuff? Then let's look at it like this. It's not an invariant, but it does measure tangledness. And it's going to be essentially what Uta was saying, which is, if we count the crossings in a given diagram for gamma, then take the average over all the angles where it's reasonable to look at gamma, then we will get this this number. And just to demonstrate, this is why it's not an invariant, okay? Because it will actually detect that this thing on the right-hand side is much more tangled. If you imagine the thing on the left-hand side as just the unit circle in the XY plane in R3, if I look at it from pretty much any angle, it just looks like a plain circle, right? It's just a bit of a useless thing in terms of being tangled. This thing on the right is isotopic to it, but if I look at it from a bunch of angles, I'm going to see crossings. Okay, so that's the idea. And the rive will notice this. It will detect the difference. Okay. So this is kind of, in my opinion, the most easy to see measure of a tangled knot, but it's not an invariant. Yes.
But I mean, like you could take a mouse, tangle it, and lots of diagrams where there are lots and lots of crossings.
Right.
If you're taking an average, you'll get.
Right. So this is the question, right? I mean, it is true. The rive can be like as big as you want, because you can just keep going. So that is kind of the question. If I want to know what my periodic orbits do, like, do they get excessively tangled? Do they get like that, or do maybe they just all look like unit circles in R3? Okay. So this is the thing. The rive is not useful. Well, not useful. The rive is not useful for knot theorists because it doesn't do the thing they want to do. It's useful for me, and it's kind of the beginning of a story that is useful for knot theorists that I won't have time to go into today. But it's useful for me because it actually measures the thing I want it to measure. Okay. All right. So this is the rive, and I think probably, yeah. Okay. The other kind of invariant, well, that thing wasn't invariant, but the other kind of knot quantity that I want to consider is a Vasiliev invariant. And a Vasiliev invariant is, well, I will tell you how to define one. So you take a normal invariant of knots, and what you do is you decide you want to evaluate it on knots that do intersect themselves a finite number of times. Okay. So this is my attempt at drawing this thing. So I've got my knot gamma doing whatever it does, and somewhere I have a self-intersection point, right? That red point. Okay, and you define your invariant on this by just taking the difference of the two resolutions of this self-intersection point. Okay, so this gives you two knots. Okay. If you want to do this for multiple self-intersections, you just do this procedure one by one. Okay, so if you have 5 self-intersections, you get an equation involving 2 to the 5 knots. Okay, That's somewhat important because the definition is an invariant is Vasiliev of finite type of order n if it would vanish on knots with n+1 singularities. So let me go back to this picture. That would mean that this kind of equation would be equal to 0. So it's telling you a Vasiliev invariant is an invariant that has some kind of relation when you switch crossings. But this relation can be very complicated if you're talking about, say, order 12, right? You're talking about a relation that only comes to light when you consider like differences of 2 to the 12 different knots, okay? But that's the idea. So they're this class of invariants that, okay, that someone chose to define, could be boring. Turns out that like most of the well-known knot invariants that you see can somehow be thought of as Vasiliev invariants, okay? So they're a very sort of strong class of invariants that, that knot theorists like a lot, okay? So if you've ever heard of the Conway polynomial or the Jones polynomial or any of the polynomials that people consider as knot invariants, all the coefficients of these things are Vasiliev invariants, okay? And again, because they were designed to detect differences in knots, they sort of measure something to do with eccentricity of it. Okay, that's as vague as I'll be. Okay, so I'm going to do essentially what Contreras did, but just for the Rive and for Vasiliev invariants. Okay, and I believe that's the next slide. Yeah. Okay, so that's the theorem. I take my hyperbolic flow, and I take a Vasiliev invariant, and canonically associated to the Vasiliev invariant is a function fv and a natural number, not 0. I don't know if people put 0 in here or not. I don't want to get into that debate. The natural numbers for me include whatever I need them to include at the time, which now is not 0. Okay, so this is what happens. The Rive grows quadratically, as we might expect, based on the linking number and it having essentially the same definition. And the constant is the same as with the linking number. The Vasiliev invariants, they grow like t to the k, where k is this k is this number that's canonically associated, and k will generally be big if the order of this thing was big. So if the number of knots you need to consider in this equation, the number of singularities that it needs to vanish on, if that's big, then k will be big. Okay, so this will grow faster if that's the case, as long as this function doesn't integrate to 0, which actually I think sometimes it could. Okay, but let me just say a little thing about the function and the number. So this is where I'm mentioning Thurston Jr. That's probably rude. This is where I'm mentioning Dylan Thurston. Okay. So there's a whole theory behind these Vasiliev invariants of how to compute them using integrals. Okay. And the story is you generalize the story for the writhing number. Okay. So the writhing number, I had to do this whole thing where I made this compactification of a configuration space. If you take much more complicated configuration spaces and you compactify them and you construct integrals very similar to the linking integral, you can build Vasiliev invariants, and that's the theory of Butt-Taub's integration. And yeah, Dylan Thurston, independently from Altshuler and Friedel, proved that this all works and found this function and this number, which I'm now using for these purposes. And yeah, the proof is going to be basically the same. So now I have slightly different measures. What I'm doing is I'm taking several copies of the periodic orbit measure, k copies of it, and I'm averaging these measures. Okay. And then I do the same thing by definition, it's asymptotic to this, which is equal to my measure equal to my integral with respect to these periodic orbit measures. Okay, so the thing that's kind of new is that we show that these measures converge to that product measure of maximal entropy. But this again, okay, this uses symbolic dynamics and thermodynamic formalism, Nima. I hope you're happy to hear that. And then again, we need to check this function is nice enough for the integrals to converge, but it is all the same structure as Contreras result, and I think we all probably want to go home. So probably, yeah, you can adapt that work to show that this function is good enough for the integrals to converge, and that is the end. Thanks for listening.
Any questions for Sully?
Yeah. Okay, so it is slightly complicated. Oh, sorry. How do these numbers? So this KV, how does the KV depend on the order of the Vasiliev invariant? So what it is okay. Can I draw something on the board? Okay, so when you want to do this whole integration procedure for Vasiliev invariants, you define a configuration space that is based on the following type of diagram. You have a big knot that is just a circle, and you have some number of vertices on the circle, and you have some number on the inside. And it has to follow some rules, this kind of picture. It has to be that everything looks like it has valence 3. Okay, and this gives you a configuration space of 4 points on your knot, and then 2 points not on your knot. Okay. There's an integral you can define over this configuration space that evaluates your Vasiliev invariant. That integral, sorry, not that integral. Once you define that integral to evaluate your Vasiliev invariant, the KV will just be the number of points that were on the outside. Okay, and the sum of these, here it's 6. I don't know what I'm saying. The sum of the number of vertices on the outside and the number of vertices on the inside is the order of the Vasiliev invariant. Okay, so generally speaking, when you try to do this procedure, you get more vertices on the outside than on the inside. That's for technical reasons. So the KV would maybe grow at least like half the order of the Vasiliev invariant. So yeah, I was kind of going to talk about this, and then I realized that it would be a whole thing to do that, and that probably we just wanted to end the conference. Not that it wasn't a good conference, but you know, people like to not have to do too much at the last talk. Yeah. So there's, oh yeah. Yeah. The integral one or the next one? Okay. So like this. Oh, this one? Yeah, okay. Oh, okay, so I'm taking a particular embedding in R3, and it sits wherever it sits, right? And when I draw a picture of it, like I'm projecting onto a certain direction, right? And what I'm saying is, if you count plus or minus 1 at the appropriate crossings in your single picture, you'll get, you'll get whatever integer you get. And if you average over all the directions where you can draw a valid diagram, so I no directions tangent to the knot itself, you will get a number, and that number is the right. So this doesn't have to be an integer, like the linking method did. Right, this is possible. It depends a lot on, well, okay, in this case, you're in S3. Sorry, I was thinking about more general manifolds. So just depends a lot on the flow, and we would need to study a lot more to know that type of thing. That's actually like the next thing I want to try and do. I don't think so. I think people have tried this sort of thing, and people that actually do knot theory, and I don't think they might. Yeah, I don't think something like the infimum or whatever would. Either that, or it would be like, I mean, I suppose it's like Richard was saying, like, for sure, like you could just make something as tangled as you want. So definitely something like Suprema would never work. Infimum, I feel like it could maybe even be 0 all the time. Because you're taking the average over all possible sort of angles. So if you just make it really sort of tightly that lines only go over each other a little bit rather than like this. You know what I mean? Like the eccentricities are not too big, then I feel like it would. But I'm not sure. Right, that has right 0 from every possible direction. Yeah. Yeah, I could believe. I think there is no not isotopic to the unit circle. Oh, what am I trying to say? At least one direction should have 0 because there's some way that you can look through all the gaps, right? I think. But yeah, the point is you're taking an average, so something. Yeah, I don't know. Yeah. The parameter t. You mean like? Oh yeah. So that's another thing I would like to understand. I currently don't know.
What's like probably over time.
I will unshare. Oh, this is very annoying.